Good morning to everybody on our webinar today. This is our UV EV Technology Magazine webinar series. My name is Jeff Peterson with Peterson Media Group. We're the publisher of UV EV Technology, which is the official magazine of RadTech North America. Today our speaker is Jennifer Heathcote, and she's going to be speaking on UV LED curing, countermeasure to the expanding energy crisis. Jennifer is a subject matter expert on mercury vapor and LED curing, UV curing systems, as well as their use across a broad range of graphic arts, product decorating, industrial coating, and converting applications. Jennifer is a current board member of RadTech North America, and she's a vice president of business development at GEW, who she currently works with. One little quick note for those as we go along the webinar today. If you have a question, everybody that's in attendance is on mute. So you'll see a little area on the right side of your screen where it says chat. So you're welcome to hit that chat button and you can put in your questions there at the end of the webinar. Then we'll take some of those questions for Jennifer to answer. So without any further ado, Jennifer, I'm gonna send it over to you.
Thank you, Jeff. My name is Jennifer Heathcote. I am the VP of Business Development for GEW. GEW is a UV curing system manufacturer. We make medium pressure mercury vapor arc lamps. We make LED curing systems, and we also make excimer/excimer, depending on where you're located, curing systems as well. We only make the curing system and some of the ancillary integration equipment. We are not a chemistry supplier. We do not formulate inks, coatings, adhesives, or any of the raw ingredients that go into the chemistry. We are also not a machine builder or a integrator of the larger manufacturing line. We pretty much focus on the UV curing system and how it integrates into the larger process. We are a UK-based company. We've been around for 32 years. We have offices in Germany and the US where I am based. Our US office is just outside of Cleveland, Ohio. For those of you who joined us about a year ago, we kind of kicked off this topic with more of an electrical grid 101. You know, for the last, 50, 60, even 75 years, for most of the Western world, energy has been readily available, it's been plentiful, it's been affordable, it's been reliable, and that really has been one of the critical foundations of why the economies have been able to grow and the lifestyles of all of us have been able to improve over those years. And so when something is so reliable, we take it for granted, right? So a year ago, we kind of did this electrical grid 101 webinar because as I go into manufacturers and I talk about the advantages of LED curing and how you can save energy, it becomes increasingly clear that most of us have no idea where energy comes from. And we just trust that the lights will always be on. And some of the global policy right now is really putting a major stress on that energy supply. And the point of this webinar is really to show that UV LED curing and UV curing in general is really a fantastic countermeasure to the expanding energy crisis. So I'm going to build on that webinar from a year ago. If you have not seen that one and really want some background into how the energy grid operates, by all means go on to UV EV Magazine's website or the GEW website, and you can watch that video in review. There's a lot of new content in this webinar, so for those of you who did watch the last one or have caught any of my presentations over the last year, this is hopefully going to tie a lot of it together. So sustainability, the way we think about it today has really been, the way we're addressing it, evolving over the last 30 years. But the concept of sustainability dates back to the late 1600s, early 1700s. The primary source of fuel, both for heat and for cooking at that time, was wood. And even all of your early industrial processes, it was wood. And it became very clear that, wood, if we completely depleted our forest, it was going to make it very difficult, if not impossible, for humanity to continue to survive in the way that they'd become accustomed to. But something else that was pointed out back then was that as we depleted our forests, the ones that suffered the most were the poor, right? The lower income level people who could not afford to purchase wood as the price points went up. So sustainability really has its origins back in the late 1600s, early 1700s around one, what do we need to do to preserve resources so that humanity can continue thriving? And then two, how do we address the market situation and preserve those resources such the most vulnerable populations can continue to be part of society and are not the ones that shelter an unfair burden of what the economy was going through. I think a little bit of that has been lost. I think today's sustainability movement is so focused on the sustainable directives for the climate, and I think some of the most vulnerable, unfortunately, are suffering. Again, that's kind of my perspective on it, but we'll talk through some of these points and kind of see how this can lead to solutions with UV curing. So while sustainability, kind of the concept, dates back to the late 1600s, early 1700s, I'll save you that long history, and I kind of jumped in about 1992. So the Rio Earth Summit was really kind of the kickoff, and that was a good 30 years ago, but that was kind of the kickoff to a global focus on environment and development. And one of the key deliverables from that was Agenda 21. You may see that come up every now and then in articles that you may be reading about sustainability and the targets. The one that I think most of us remember, or at least those of us who were working in the 90s, is the Kyoto Protocol, which that took place in 1997. And the product of that was a international treaty that was enforceable in 2005. But you have to keep in mind, international treaties, while they say they're enforceable, they require every party that signs on to it to go home and pass legislation in their respective country or their economic region that makes that country, that region, compliant with the terms of the treaty. Unless that legislation happens, there really isn't a way to enforce the objectives and the deliverables of that treaty. So the Kyoto Protocol was 1997, and keep that date in mind because it'll come back up here in a couple slides, as well as that 2005 year where that was meant to be enforceable. And that was really when everybody started talking about greenhouse gases and the need to curb those emissions in order to reduce or curtail climate change. From there, the main one that I think many of us refer to is the Paris Agreement, which took place in 2015. And that expanded that work on the Kyoto Protocol. And that was when the metrics really started to come out. This is where that keep global warming to less than 2 degrees C, and everyone needed to work to be net zero by 2050. So we often hear these phrases, and you need to understand that while it dates back to the Paris Agreement, it really goes back even further, the Kyoto Protocol and the Rio Earth Summit. As I mentioned, though, that these international treaties, they only really have an impact if the parties of that treaty go home and pass and get their legislators to pass legislation. And so even though you would hear about it from maybe the big brands, from the NGOs, from the activists, from a business perspective, other than maybe trying to purchase some wind and solar power, not much was happening until the past couple of years. Many of you are starting to hear either internally when you're in your organization or from your customers, the need to document what your scope 1, scope 2, and scope 3 emissions are. And up until recently, this has all been voluntary. But what's happening is that countries, economic unions, are running this climate change objectives through the financial regulatory bodies. So right here, you've got the UK, the EU, and the US. And the way these targets are being administered is through the financial reporting. So if you work for a publicly traded company, if you are a publicly traded company, or you are part of a larger financial portfolio that is traded on any sort of stock index, they're using the financial sector to require these companies to report scope 1, scope 2, and scope 3 emissions in any, it varies by country, but that's where this is coming from. So again, the reason we weren't hearing too much about this is because these laws really are only starting to go into effect between 2019 and 2024. The final row on this table refers to the United Nations Framework Convention on Climate Change. Now, the Conference of Parties, basically anybody who's a delegate or a signatory on these treaties, will attend these meetings. Last year, it took place in Egypt in November of 2022. The next one will be in Dubai in December of 2023. And so out of these meetings becomes the next kind of the agenda and the directives that people then go back to their countries and try to get this legislation implemented. Last year in 2022, basically the main outcome from that was that there was a commitment to do climate reparations to the third world. In other words, the position from the COP27 was that we didn't want the third world to invest in coal and even natural gas, and that we would subsidize the installation of solar and wind in the third world so that they could skip all of the greenhouse gases that we emitted and go straight to solar and wind. The challenge is that the third world doesn't want that. The third world wants coal, the third world wants natural gas because it is much more reliable than the wind and the solar that are being installed in those regions. So you're starting to hear things like, you know, climate colonialism. And so there's a lot of backlash right now because what the first world wants and what the third world wants is very different, because ultimately energy is what lifts people out of poverty. And so we've got conflicting forces right now where half the world is focused on climate change and keeping temperatures low, and the other half of the world is just focusing on wanting clean water and the ability to not have to wash your clothes by hand and pump your water by hand and cook your food with, you know, wood and animal dung. So we definitely have differing views on kind of what the direction of energy policy and climate change is in the world. So how does this kind of affect us on a, you know, corporate, or kind of how did this evolve in this and how we're going to strive to meet this net zero by 2050? Well, out of 2015 in the Paris Climate Agreement, the idea was that you would go back and install solar panels and wind turbines on your property, and you would try to make yourself as independent from the grid as possible. The challenge is that solar and wind just aren't very energy dense. So as a result, it becomes very difficult to pull enough power, enough reliable power to run manufacturing operations. You can do it for, you know, low level lighting, you know, some manufacturing process, but anything that's energy intense just needs a lot more electricity. And then there are certainly applications that cannot run on electricity. So anything that was diesel, anything that you had to use hydrocarbons, if you couldn't electrify that with solar and wind, you had to offset that somehow. So it shifted to do everything you can to be carbon neutral, but then offset anything so that you could refer to yourself as net zero. The challenge there is that even today, if the UK were to double its forest land, it would only offset its carbon footprint for 2 years, right? And so then what do you do? I mean, you can't make your entire nation a forest. I mean, people have to have somewhere to live and work and play. And another example is Amazon. If Amazon were to offset its carbon emissions, it would have to plant trees in the size of an area the size of Costa Rica every single year. So there's just not enough land to plant trees to offset these carbon emissions. Carbon capture just is not commercially, technically, practically viable today. So this objective of offsetting and installing solar and wind really is not going to get us to net zero by 2050. So then the shift came to, well, how about carbon equivalence? So carbon equivalence is I'll contract with my utility, I'll contract directly with a solar and wind farm located somewhere where there's lots of wind or lots of sunshine, and I'll be able to purchase that electricity, even though the electricity that's feeding my plant is coming from the nearest generator. If that nearest generator is a coal-fired plant, a natural gas plant, a hydro dam, a nuclear plant, a solar farm, or wind farm, your power in your facility is coming from the closest generator to you. Electrons are going to flow through the grid and follow the path of least resistance over the shortest distance. So renewable energy certificates were invented so that you could contract and purchase these energy certificates to offset whatever portion of electricity you were getting from non-renewable sources. So renewable primarily meaning, you know, solar and wind, although sometimes biomass gets lumped into that as well in some countries, but definitely not coal, nuclear, and natural gas. So we now find ourselves in a situation where we're just not installing enough solar and wind, and there's a lot of complications from the engineering and the practicality of installing, large wind farms and large solar farms. And we're getting lots and lots of regions are actually rejecting them. So we're just not building enough solar and wind to, provide companies with enough solar and wind power to say that they are net zero. In fact, what we're doing is, as we retire nuclear generating facilities, the solar and wind that we're adding is pretty much just offsetting the nuclear retirements. And so we're not really getting a whole lot of benefit in carbon reduction because nuclear wasn't emitting any carbon anyway. And a lot of the coal plants that are being added in China and India and Indonesia are actually generating a lot more than we're taking off of the environment in Europe and North America. So then came the concept of absolute zero. So if we can't use, carbon neutrality and we can't use carbon equivalence, how do we get to net zero in 2050? Well, this is taking it to the extreme. So this is a no carbon attitude. In other words, everything you do has to be zero emissions, and you can't negate that with anything else, right? You can't go plant trees, you can't use carbon capture if it doesn't really exist yet today. Hydrogen is talked about, green hydrogen, blue hydrogen are often talked about, pink hydrogen is talked about. Those are just the color codes of how environmentally friendly it is. It's still hydrogen. So the idea is go to zero emissions wherever we can, reduce the amount of energy we use. And this study was particular to the UK. And so the idea was through this study, or the conclusions were that in order for the UK to be net zero by 2050, they would have to reduce the amount of energy they use to a 60% level of today with no growth over the next 25 years, and restrain emissions for basically the next 25 years in order to be able to say we're net zero by 2050. So I'm not on board with this because this is not a pro-growth strategy. I mean, this is clearly negative economic growth. What they're suggesting is that in order to be net zero by 2050, we have to move everything to the electrical grid, which is why you're seeing a lot of your, customers or maybe your facilities trying to move anything you can to an electrical source of energy, not use natural gas, ban everything that cannot be electrified. So right now there's 4 main categories that you cannot run on electricity. That's airplanes, that's cargo ships, all cement production, and beef and lamb. Beef and lamb emit methane gas when they through their digestion process. So this is why you're hearing, kind of in your news feeds about the desire to get rid of all beef and lamb, and there's a lot of countries that are passing laws to get rid of, all farming related to beef and lamb. Cement production, we use cement everywhere. I mean, there really is no alternative in some cases, but the idea is to no longer use cement and pretty much stop all international trade, because if you can't fly things on planes and you can't, transport things on cargo ships, if you thought that the 2 years of rolling lockdowns during COVID were disruptive to the economy, 25 years of no international trade, if that's what it's going to take to get to net zero, then we are clearly in trouble. The last 3 points with absolute zero is that it would rapidly expand non-greenhouse gas emitting electrical generation, which is primarily solar and wind, and then close all power plants that emit greenhouse gases. So that's coal, oil, and natural gas. But the last bullet point I think here is very insightful, because they also say that we have to design an equitable market for sharing an insufficient supply of non-emitting electricity. In other words, they fully acknowledge that there will not be enough energy to go around. In this case, for the UK, they have to operate on 60% less energy than we have up until now. Every year, energy demand goes up. It's not going down. As China, India, Southeast Asia, as people move into a higher level of living, they want more energy, not less. So if you want to understand this absolute zero a little bit better, I did put a video link at the bottom of the slide. You can watch the professor that's kind of behind the absolute zero study explain what this entails. There's also a paper that was written, and the link you can find at the bottom of the slide as well. I don't expect you to read that slide on the right, but it's very recognizable if you go to that paper. They go market by market, so they look at road vehicles, they look at rail transport, they look at airplanes, they manufacturing, power generation. They go through each of these categories. Each of them is a different color. And they look at it between, 2020 and 2029, and then 2029 to 2050, and then, after 2050. And you can see those three red circles, towards the right. Pretty much that is airplanes, cargo ships, and at the very bottom, that's fossil fuel generation. And absolute zero pretty much means we have to get all of that off all of that completely. And so my comment often to executives, if when we talk about sustainability, is what's your negative growth plan, right? Because net zero by 2050, assuming an absolute zero agenda, means that all of us have to restrict. So your manufacturing, your operations, your sales, your everything has to constrict. And I'm still in the pro growth category. I'm still neoclassical economics. This image you see on the left is kind of what does this mean for manufacturing? So if the orange column on the left is moving everything we can to today's technology and banning, again, airplanes, cargo ships, cement production, beef and lamb, how do we then shrink down to about 60% of current energy? And that's by making everything we do last longer. So cars, industrial equipment, so all your manufacturing lines, the clothes that we're wearing have to last twice as long. We also have to reduce design and product size. So use less material, shorten our manufacturing lines, use more energy efficient products, avoid overuse, right? Only use what you need when you need it, and then reduce scrap. And so what I'm going to talk through for the rest of this presentation is how UV curing in particular, whether you're on board with absolute zero or not, and I am not, I am definitely pro-environment, I definitely want clean air, I definitely want clean water, and I want to make sure that future generations have access to the same resources, but I still want a pro-growth society. So UV curing is a way to kind of tackle some of these objectives with an absolute zero to reduce our greenhouse gas emissions, but still grow our companies very successfully and very responsibly. So where are we seeing all of this legislation? Well, we talked about the three financial bodies within the UK, the EU, and the US that are pushing the mandates for reducing greenhouse gases. And it's all based on the greenhouse gas protocol. And anytime we start to see things, the first thing I do is I always kind of go back and try to figure out where this started, because I only really started hearing about scope 1, scope 2, and scope 3 last year. And so it's easy to think this kind of came out of nowhere and is something new. And if you haven't heard of it, basically it's taking account for the different parts of your organization and upstream and downstream where you're generating greenhouse gases. And I list the greenhouse gases on the left. To most people's surprise, water vapor is the single largest greenhouse gas in the environment, followed by carbon dioxide. We often talk about reducing your carbon footprint because a lot of fossil fuels, hydrocarbons, contain carbon, and carbon dioxide next to water vapor is the largest greenhouse gas, followed by methane, nitrous oxide, and then the others that you see there. So a lot of our manufacturing processes, a lot of the vehicles that we drive, release those greenhouse gases into the atmosphere. And the more greenhouse gases we have creates that buffer that allows the earth to heat up. It's there for necessity, right? Without the greenhouse gas, none of us would be here today. We do need greenhouse gases to provide the warmth and provide the environment in which we live. The argument is that as those greenhouse gases become too much, that the temperatures escalate, and by reducing them, we can bring those temperatures back down. So scope 1 has to do with everything that your company is doing that releases greenhouse gases directly into the air. So that's anything that's released from your manufacturing facilities, as well as the vehicles that you drive. Scope 2 is purchased energy. So anything you're purchasing for use, so it's purchased energy, electrical energy, hydrocarbons, heating and cooling, purchase steam. I was surprised to learn that scope 1 and scope 2 were introduced in 2004. And from that first slide, I told you to remember the date of the Kyoto Protocol. So the Kyoto Protocol in 1997 was followed in 1998 by the two NGOs that you see on the right, World Resource Institute and World Business Council for Sustainable Development. They kind of came onto the scene in 1998, right after the Kyoto Protocol, to try to figure out ways to measure, monitor, and standardize greenhouse gas reporting globally. And in 2004, they came up with scope 1 and scope 2. Scope 3 didn't really enter the scene until 2011, and that basically looks upstream and downstream. So many companies have been reporting scope 1 and scope 2. Again, if you're a large financially traded company, you've kind of been aware that this was coming. Scope 3 is really just now starting to take effect. And if you're a supplier, I'm sure many of your customers are starting to call you asking for your scope 3. And that's where this is coming from. If you are a large publicly traded company, or just a large, very large multinational company, you are required, by law now in 40 different countries to start reporting this information. So this is where it's coming from. So in the US, it's being handled by the Security and Exchange Commission. The UK, it's being done through Streamlined Energy and Carbon Reporting. And then the EU, it's through the European Baking Authority. There's different dates, and the actually how this is implemented varies, by each of these countries and these regions. But the dates are, 2023, 2019, 2024. So it may seem like this kind of came out of nowhere overnight, but this has been 30 years in the making. It actually goes back to the Rio Summit in 1992. We are a good, 30 years into this. People who know me, I measure things in decades. I mean, we all work in business and we always want to meet revenue, we always want to grow and introduce new products and year to year. But if you step back and you look at things in a decade, it's easier to make sense out of things. And things always take a lot longer, than we think that they do. And so I tend to look at things over decades. And as you can see towards the top, the variations of this scope 1 and scope 2, scope 3 reporting do vary by country and region, but it's now law in some way, form or another in 40 different countries. So there's another version of scope called scope 4. It is part of the Greenhouse Protocol, but it is completely voluntary. It's relatively new. Not a lot of people are aware of it, but it refers to avoided emissions. Avoided emissions, or scope 4, is how do you capture, the positive aspects of a product or a process or a technology that may not be captured in scope 1, 2, and 3. And I borrowed this image on the right from the World Resource Institute. They're the ones that came up with this. And the idea is you compare an older version of a product to a new product, or an alternative technology to a current technology. And you can compare the greenhouse gas emissions over the lifetime of that product. And that would include everything from material acquisition and pre-processing, production, distribution, storage, use, end of life. And this is where UV, and particularly UV LED curing, have a huge advantage. I mean, the scope 4 avoided emissions for our technology is, really has potential to make companies meet their targets a lot easier. Again, I don't think anybody's really going to be meeting net zero by 2050 unless we just quit using the energy that I talked about. But I think all of us have a vested interest to do the best job that we can. And I do believe that UV and UV LED in particular will become an increasingly big part of manufacturing operations going forward. And I'm going to address that here in the coming slides. So how do we segment kind of where greenhouse gases come from? Well, we can look at the electricity supply, we can look at transportation, and we can look at industrial processes. I think for the last 20 years, there's been a real big emphasis on electricity, right? Let's just start building as much solar and wind as we can. Let's retire our nuclear power plants. Let's retire our coal plants. In the US, we've seen the biggest drop in greenhouse gas emissions because as we've retired coal plants, we've shifted to natural gas. I mean, that's really where most of the greenhouse gas reductions have come, is from going from coal to natural gas. But natural gas still contains carbon, it still is a greenhouse gas. So there's still a lot of pushback that says you can't even use natural gas. But unfortunately, solar and wind just aren't plentiful and they're not energy dense enough to replace that source of energy. So today, oil, coal, and natural gas still provide 84% of all the world's energy and about 64% of the world's electricity. And the balance above 64% is not solar and wind. It's predominantly hydropower. So it's dams, it's pumped storage. Solar and wind are still only about 13, maybe 14% of the world's energy supply. And there's a lot of speculation that it's not even possible to make them more than 50. There's just limitations in the technology. And after 20 years and 5 trillion USD investment globally, hydrocarbon use only decreased by 2%. It is the reality of the situation. Hydrocarbons are just so energy dense, and the way we live our lives today are so dependent on being able to harness that energy that there just aren't that many alternatives. We can use them smarter, but it's very difficult to get them to go away. So as a result, we all refer to this, often you hear it referred to as the energy transition. There's a lot of people that have started saying, we're not in an energy transition. A couple percentage difference is not a transition, it's an addition. And that's effectively what we're doing. We're adding solar and wind, we're retiring, coal, we're not investing in natural gas, at least in Europe and North America. And all the solar and wind is really doing is offsetting some of the nuclear that's been retired. Meanwhile, the rest of the world is trying to catch up. And so they're building a mix of the technology. They are building coal plants, they are building nuclear plants, they are building natural gas plants. Then we look at transportation. This is rail, this is earth moving equipment, this is cargo, both ship and truck, it's airplanes, it's passenger cars. Oil powers 97% of global transportation, and it will continue for a while. Diesel is just energy dense. It's incredibly rich, and it's just not possible to move any of this to the electrical grid. Where you're seeing electric vehicles is really passenger vehicles, and it's not even the primary household car. Typically, it's the second car or the third car, which is driven less, which means even switching to electrical vehicles, unless you make that your primary car, you're really not even doing much to reduce the greenhouse gas emissions. So transportation, there's not a whole lot we can do there anytime soon. Airplanes can only go about 200 miles on a battery. So industrial processes is where we're starting to look. And unfortunately, breakthrough technologies are not commercially viable yet and will likely not be at scale by 2050. So this is carbon capture and storage. Yes, there's a lot of innovation, but there's still nothing really commercially viable. So if you think you can pull carbon out of the atmosphere, out of your processes and store it, it's definitely something that we need to investigate, but it's not something that you could launch today. Battery technology is still in its infancy. We do not have grid level batteries in mass, and the amount of mining that it's going to take to produce the cobalt, the copper, the rare earth metals to make batteries in mass production, we're a long way off. And then green hydrogen is another one that's often talked about. So you can pull hydrogen out of water molecules and use it as a fuel. They color code it, whether it's green, blue, gray, pink, based on how energy efficient it is. So the idea of producing hydrogen using green technology means that you would use all of the energy to produce that hydrogen would have to come from solar and wind. So the challenge with going to green hydrogen is it takes 1.5 units of energy to produce 1 unit of hydrogen energy, and it's very intensive. And we already don't have enough solar and wind to supply our current manufacturing processes, and now we're going to introduce, a more energy intensive production process for energy. So it's just this loop that just does not make sense. 2 + 2 in this case is trying to add up to 10, and we're barely at 2 + 2 = 4. So the challenges with solar and wind is that they're spiky, intermittent, and seasonal. If you look at the profile on the left, we have to make a solar farm that is only generating energy when the sun is shining look like the profile on the right. The profile on the right is what the current electrical grid does. Oil, natural gas, particularly coal is baseload technology. It is the steady state 24/7 production of power all day long, big centralized power plants, right? Intermittent is kind of how it fluctuates during the day or over, the course of a month or a year. And then peak load is that rapid change. How do we have to adapt to changing electrical demand through the course of the day? And that's really met best with natural gas, diesel, oil. Solar and wind really fit best in that intermediate. We can balance it because it's not a steady supply. And if you look at the image on the bottom, that kind of shows you where battery technology is today. This is a converter in California. They have 3 power pack batteries, each at 174 kilowatts, and 1 inverter that switches it from AC and DC. This takes up a good 2 parking spots in his facility, and you can run your machine for maybe about an hour, right? And then it has to recharge. So battery technology is still a long way off. Certainly we need to continue innovating and exploring it, but to think that we can use battery technology to even out that yellow spiky profile, we're just not there yet. And then the natural capacity factor. This is how much energy a generator can produce, giving the site conditions, assuming no technical failure. So if I'm assuming that the parts aren't going bad, that everything is operating correctly, given the site conditions, how much energy can I generate? And the global average for solar is between 11 and 13%. So nearly, 85 to almost 89% of the time, those solar panels aren't generating power. They don't generate at night. They don't generate on a cloudy day. They don't generate during a storm. Wind, we're about 21 to 24%. Whereas thermal generation, whether it's coal, gas, nuclear, oil, we can pretty much generate power between 90 to 100% of the time as long as we have that fuel. What this means is we need a lot of land to install solar and wind. And so the environmental movement that I grew up with that was protecting land, protecting forests, protecting the oceans, protecting species, right? Protecting the eco-diversity of the environment, that's kind of dead. I mean, solar and wind are pretty much taking over wide swaths of land, and we're basically only at 14% generation, globally. So you are going to see solar panels and wind farms everywhere in order to meet, the demand. And there's a lot of pushback from those rural communities because they feel like they're sharing an unfair burden of having to give up their land to have these installed. And then energy density, nuclear, natural gas, hydro produce a lot more energy per site, per the land that they take up. This is 4 studies. Don't get too hung up on the numbers, but 4 different studies that took account of how much land was needed, including mining, buildings, locations, setback areas, how much space was needed to generate power. And when you look at these numbers and any one column, granted the columns differ from each other because there were 4 different studies, but they all show that nuclear, natural gas, hydro, and coal, if I were to have included that, generate so much more energy per land, right? It just doesn't take up as much land to produce as much energy. So as a result, you need a whole lot more solar and wind to produce the same amount of power. Now, the trade-off is that, nuclear has its, the environmental concerns of the waste. Natural gas and coal certainly produce greenhouse gas emissions, but solar and wind are not necessarily environmentally friendly. What they look at is the fact that the source of energy, the solar, light, the wind, is renewable. But the carbon footprint for solar and wind production is actually not that great either, and their lives are pretty short. As you can see here, wind turbines only have about a 12 to 20-year life. We've pretty much built them as big as we can build them. They can't really handle the stressful environments that they're being put into, particularly ocean water, right? So they're degrading very, very fast. And right now there's no way to recycle them. So the turbines are taken off of the windmills. They're stripped for the metal that's in them they can get out. But that fiberglass, the balsa wood that's on the inside, pretty much they're being stored in old industrial manufacturing lots and then buried when they can. And it's the same thing with the solar panels. Now, I see a lot of metal in this photo on the right, and you certainly think that that could have been recycled. And there's tons of photos like this on the internet. I just grabbed one that I thought kind of made the point. But the idea is that, we can make a coal-fired plant, a natural gas plant, a nuclear plant last upwards of 60 years. And in this case, we're having to completely replace the technology anywhere between 12 and 30 years. And then the revenue stream is very different. So thermal generators, coal, natural gas, nuclear, they make money by selling electrons to the grid, right? But wind and solar, they not only make money by selling electrons to the grid, but they also sell the renewable energy certificates we talked about earlier, and they also get tax credit subsidies. In many cases, solar and wind can sell power to the grid at 0 cost. And they can even pay the grid to take it because they're making money off the renewable energy credits and the tax subsidies. So as a result, there is a huge disincentive to continue building in Europe and North America traditional thermal generators because they just can't compete because the revenue streams are quite different. So the EPA proposed new rules for power plants in the US. These are rules. Once they are accepted, which they are about to be accepted in some form later this year, early next year. And again, we're going through government agencies. In this case, it's the US Environmental Protection Agency to put rules in place on the generating plants. And the EPA is basing this on breakthrough technologies that don't really exist yet. Carbon capture and sequestration, co-firing a coal plant with natural gas, co-firing a natural gas plant with clean hydrogen. And I won't bore you with the details, but pretty much we're constricting the ability of our coal and natural gas plants to produce power over the next, pretty much from now going forward. They were all going to have their hands strapped. And a lot of these rules really don't have a practical implementation. It's a broad mandate for every state in the United States, and not all states even are on land where you can store carbon underground. And there's not a single commercially, installed example of, carbon capture for a power plant right now. There's some great things that are being worked on, but these laws take place right away. So we're going to see a lot of the power feeding the grid, if this goes through, is going to become very, very limited compared to what it is today. So we often hear how it is the cheapest way to produce energy is solar and wind, and that's a true statement. If I draw my bubble or my zone of evaluation around my generating plant, because what they're referring to is the levelized cost of electricity. It's the average cost of electricity generation for a generator over its lifetime. If I just look at that purple circle, once I have my solar and wind farm in place, I don't have to purchase fuel, right? The sun shines when it shines, the wind blows when it blows. I don't have to purchase coal or uranium or natural gas. So in that respect, yes, solar and wind are absolutely more affordable. Problem is that what we really care about is the full cost of electricity. That is what is the ratepayer playing, because that electricity has to go through the transmission lines and then through the distribution. The electrical grid is made up of generation, transmission, and distribution. Generation, at least in the US, is deregulated. So you can have private companies building and running power stations. 30% of the US is still vertically integrated in the monopolies of, that we've had for the last 100 years. But the cost to build the transmission lines is expensive. We don't have enough transmission lines. There aren't enough transformers. And the state laws that require the balancing of all of the renewables to take precedence over thermal generators is making this very, very expensive. So by the time that low cost solar and wind is getting to your facility, it's, the rates are just rising, and they're going to continue to rise because we're also basically retiring nuclear, coal, and not investing in natural gas. So the full cost of electricity is what we care about. And what you see in articles is the levelized cost of electricity, which doesn't give us the full picture. So how do you, as a ratepayer, both at home and in your company, mitigate those rising energy costs, reduce your energy demand, and curb greenhouse gas emissions? Well, let's take some insight from Milton Friedman. This is a quote that kind of circles around, and Milton Friedman said it best when he says, "Only a crisis, actual or perceived, produces real change. When that crisis occurs, the actions that are taken depend on the ideas that are lying around." Now, he was talking about public policy. He was talking about think tanks. He was talking about academia. He was talking about creating ideas so that when a crisis happened, you had lots of them to pick from, and you can implement the one that made the most sense. We can apply the same concept to technology, right? Today, we are in an energy crisis. Today, the climate change crisis is forcing us to make decisions to reduce greenhouse gases. What is the technology that you can implement today that will reduce your energy demand and lower your greenhouse gas footprint? It's not breakthrough tech. Breakthrough tech, carbon capture, green hydrogen, battery technology, it's just not ready yet. By all means, keep working on it, maybe in 2050. But what we need to do today is figure out what's the technology you as a manufacturer can implement today that can offset the net zero, absolute zero, ESG, geopolitics, war mandates that are causing insufficient supply, grid instability, blackouts, and rising costs. What is that solution? Well, I truly believe, and I'm not just saying this because I'm in this industry, but UV and UV LED curing is established technology that exists today that you could implement in the next 3 months. You could have a manufacturing line up and running with UV curing that will mitigate your energy costs, lower your energy demand, and reduce your greenhouse gases. It already exists. It's been around for decades. Obviously, LED is a little bit newer, but it is a solution. It's a photochemical reaction that harnesses energy stored in wavelengths of light to set and adhere your inks, coatings, and adhesives and extrusions in manufacturing processes by reacting the molecular bonds. Nothing is evaporated. There's no water, there's no solvent that has to be emitted into the air. The materials are 100% solids. It's a chemical reaction that occurs instantly. UV curing has always been environmentally friendly. It reduces scope 1, scope 2, and scope 4 emissions. It cures instantly at fast line speed and a small footprint. So remember that graphic I told you that said that we have to make things last longer and use less space. So they don't want you building new buildings. And if you do build a new building, you need to make it as small as possible. So shrinking your manufacturing lines is one thing that you can always do with UV curing. There's no solvent chemistry, no thermal oxidizers or afterburners like you see in the bottom right. If you're using solvent technology, you have to burn off those emissions before you release them into the air. There are no emissions with UV curing. So automatically your greenhouse gases are reduced. There's no hazardous air pollutants. You reduce your energy consumption. Because it improves process control and because it's a shorter footprint, you can make your make ready becomes shortened, right? So there's less scrap. Process control means there's less scrap in production. You can ship and finish products quickly, so there's less work in progress, less storage. And because the chemistry doesn't contain solvent or water that must be flashed off, you're reducing your transit and storage weight and volume of the formulations. And it also extends the useful life of the final product, robust mechanical and chemical properties. You may not get the same level that you would with a solvent, but it's good enough. And if you can start moving some of your solvent applications to UV, that'll free up capacity on those lines because you're not getting additional permitting for those processes. So we're seeing a lot of companies want to move from solvent to UV where it makes sense. And eliminate those thermal oxidizers and those long drying tunnels. So UV LEDs use less energy, less electrical energy. This chart compares a full cure arc lamp, a microwave lamp, a full cure LED system, an inkjet pinning lamp. If I go left to right, you can see the peak irradiance. Obviously, LED has a much higher peak irradiance than a conventional arc lamp, but the category, the column that we're most concerned about is the one that's watts per centimeter. How much energy in per length of lamp does it take to operate that system? And if you compare the full cure arc at the top, which is between 80 and 240 watts per centimeter, and the microwave lamp, which is also between 80 and 240 watts per centimeter, compared to LED, automatically the power in is a fraction of the requirements that you do with conventional UV. So I can also compare this to a thermal generation, right? If I compare a solvent process or a water-based process to UV and then UV to LED, it's all a matter of how much energy am I using to make this process work and how much of my greenhouse gases am I emitting through my stack. And UV, as you can see the benefits on the right, there's so many aspects of UV curing that help this help you achieve the scope 1, scope 2, scope 3, scope 4 emissions requirements. This example, many of you have seen me use this before. I probably need to come up with some new ones, but this is a really good one. And it compares for a narrow web flexo press. It's an 8-station narrow web, so 45 centimeter wide flexo press, powered on the left column shows a mercury arc system. The center column shows a water-cooled UV LED system, and the right column shows an air-cooled UV LED system. And if I just compare the power left to right for the whole UV system, you can see that on the conventional air-cooled system, I'm at 62 kVA. kVA is another, it's a slightly different way of writing, watts. So just think of it in terms of power, and a bigger number is not as good as a lower number. So 62 kVA for mercury arc. When I go over to LED water cooled, I can add these two together for the electrical power and the chiller. I'm at 52, so 62 to 52. And then when I go to air cooled LED, I drop down to 26 kVA. So as that power goes down, I'm using less electricity from the grid, right? So automatically I'm reducing my cost of that energy because I'm using less. I can also, regardless of where that power is coming from, whether it's coal, nuclear, natural gas, solar, wind, I'm using less. Less is always good, right? It frees up capacity for the rest of the grid. I'm also, reducing, if that's coming from a coal plant or natural gas plant, by using less, I'm reducing my greenhouse gas emissions because I'm avoiding emissions, right? And then you look at that bottom line. Your main objective may be to reduce your carbon emissions, but by doing this, you're also reducing your cost of operations, because by using less kilowatt hours over the course of the year, I can reduce my energy consumption 66%. Now, this example is for a narrow web flexo line. We can extend this to just about every application, every market. Some numbers are a little bit more attractive than others. It really depends on the application and how you're using it. I'm going to wrap up here. I think this slide and the next slide are my last ones, but this kind of summarizes the title. UV curing, whether it be conventional arc or LED, is a countermeasure that is available now. If you go back and look at what I showed you on slide 5 and slide 7, slide 5 was absolute zero for manufacturers, and slide 7 was your scope 1, 2, and 3 emissions. Both conventional UV and UV LED are incredibly attractive. They are all electric, which means there are no greenhouse gas emissions at the operating site, right? There's nothing going out into the atmosphere that I have to report. The chemistry is 100% solids. By using that chemistry with a UV system, I'm not evaporating anything, any solvent that has to either be incinerated or released to the air. So there's no greenhouse gas emissions from the chemistry. The equipment and manufactured good last longer. Goal is twice as long. So again, LED systems don't have bulb technology, right? So you don't have to replace the lamp. There's no consumables. So if I just look at the manufactured production tool, LED is going to last longer. If I have to change a mercury arc lamp every 1,000 hours or so, I might be able to get, depending on my application, 20, 30, 40, 50,000 hours of an LED system. This is what we're being told to do by the mandates. And LED technology is that existing technology today that you could put in your manufacturing process. If we started talking today, in 3 months, you could be up and running for many applications, LED. Reduce over design and size of your manufacturing line by 1/3, right? Well, if I compare that to a solvent line, a UV line always takes up a lower footprint. We are seeing a lot of companies that have always been in the solvent realm, and even in the water, based realm, that need to shorten their manufacturing lines. Both conventional UV and LED, they do that. Use the most energy efficient, best available technology. Well, hands down, that's LED. Conventional UV is not too bad either, but LED definitely starts to get those efficiency numbers where the mandates want us to be. And limit overuse, right? Don't over design anything. Both solid state technology with conventional UV and LED allow you to dial in the power level, allow you to do the correct number of lamps for the manufacturing speed. There's no reason to put more power into that line than you need. And then certainly by shortening the lines and using UV, you're going to reduce your make ready, right? So there's less scrap, there's better process control. So UV just ticks all of the boxes. I think it's the perfect product for manufacturers to turn to. And in the words of Milton Friedman, it is that technology that is lying around today that is ready to go. So I'll conclude by saying that if greenhouse gases are the metric, and they are, clearly everything we're being told is that greenhouse gases are the metric, and reduction is being mandated and non-compliance will be taxed, then UV curing, and especially UV LED curing, is the clear winner compared to alternative technologies that consume greater amounts of electricity and by default emit greenhouse gases and hazardous air pollutants during their operation. So a couple of citations for those of you who want to delve into anything that I mentioned a little bit further. And with that, I will conclude. And I think we do have a few minutes left for a couple questions if anybody has them.
Okay, thank you, Jennifer, very much. I do have a couple questions here. So here's one for you. Are you seeing companies, Jennifer, migrate from solvent-based technology to UV? I know you're talking about the advantages. Yeah. Are you starting to see that out in the marketplace?
Yeah, we are. I think in general, we're getting inquiries, but I think where we're seeing the most activity right now and most interest is in UV hot melt, right? So a lot of your pressure sensitive adhesives that are used globally around the world for a wide variety of applications, industrial applications, packaging applications that use hot melt, they're making the decisions to get away from solvent, either because they cannot get additional permitting, right? So moving solvent technology that doesn't need to have the same performance requirements as a solvent-based to a UV, which will get you just good enough. We are seeing that. We are doing a lot of demos, a lot of testing, and quoting a lot of systems, particularly in UV hot melt, but in other applications as well.
Okay, another question. Where are you, and maybe this is a little bit of the same thing, but where are you seeing the most market growth or potential for both conventional and LED?
So printing has always been one of the biggest markets for UV curing, right? Whether it's a narrow web flexo press, whether it's a sheet fed offset press, whether it's a web offset press, inkjet, screen. I think all of the printing markets can go LED today, right? There may be a few functional aspects of that maybe aren't quite there yet, but the bulk of those markets are shifting from UV to LED. And we look at South America, so much of South America is still water-based. And we're seeing a lot of South America want to just skip the conventional UV and go straight to LED. So printing is definitely by far, one of the major market segments. All the functional chemistry that use conventional UV, we're still in some sort of a product development stage to switch a lot of that to LED, but I can tell you that I am working closely with formulators across all the different market segments to develop chemistry to work with LED. So while printing probably still has the bulk of it today, I think that's progressing more into coatings, definitely adhesives, and certainly industrial applications that aren't even aware that UV technology exists. We're starting to have those conversations.
Okay, here's a question. Is there a place we can see an actual comparison between conventional and LED curing systems in terms of the power consumption?
Yeah. So that's a really good one. Probably the best place to see something like that is on a narrow web flexo press, right? Because narrow web flexo presses can use what we call arc led technology that allows the arc cassette and the LED cassette to swap back and forth, quickly, within, 10, 15 seconds, you can switch between the two. So a lot of your OEM narrow web flexo demonstration units, either at their facilities or at the shows, are starting to demonstrate that. And I am aware that if for those of you that are going to Label Expo, I believe Mark Andy is planning to do that on their booth, is that they will have a press that can run both arc and LED, and they're going to show the actual current consumption in real time as it's running, because that's really powerful. It's one thing to sit here and have me say it. It's another thing to actually see the current consumption in real time.
Great. Here's one about E-beam. How does E-beam compare to UV LED, given the lack of PLS?
Yeah. So E-beam is a sister technology of UV. GEW does not make E-beam systems, but E-beam is also incredibly environmentally friendly. Pretty much everything I said about UV also applies to EB. The big difference between UV and EB is that the EB systems do not contain photoinitiator in the formulation, whereas UV does. That's what the light is reacting to. Another difference is that the E-beam systems require nitrogen. You have to do it in an inverted environment. So you'll have a nitrogen component with E-beam. And the E-beam systems are really limited to web, right? So you're not going to run a 3D part through an E-beam system. It's probably going to be a web, whereas UV technology, arc and LED and microwave can be used with 3D parts, web, and sheet as well. But certainly E-beam has just as good as an environmental story as UV and LED.
Really, my question, why is E-beam limited to web and it's not?
Yeah, it's primarily because of the nitrogen environment, right? You're generating electrons that have to travel through a gap to reach the ink, coating, adhesive, whatever it is you're trying to chemically cure. And you have to do that in an inert environment. If you don't, then the electrons aren't going to do their job. So it is easier to keep that inert environment tight with a web versus sheets, which are going to be fed through an open gap, and they're going to be pulling a lot of atmospheric oxygen into the process. So nitrogen is just easier to do with a web than it is with a sheet. And without the nitrogen,
I think we have time for one more question. Do you have a side-by-side showing how solvent lines compare in the zero guidance, the traditional and LED radiation cure?
So this question comes up all the time, and we need to do one, and we will do one. All solvent processes are so different from each other. The tunnel dryers are all so different. It's hard to do one calculation that kind of captures it all, but I think we're at that point where we need to do it. I think we need to start showing people the real numbers, because it does come up, and I've kind of committed to at least pushing that through here in the next 6 months, because I think it's important. Because if you are running a tunnel dryer that's powered with natural gas, you are going to be you're going to be mandated to move away from that. I mean, you look at the earlier slides, I said they do not want us using hydrocarbons if we can move away from them. So a long tunnel dryer that might be, 20, 40, 60 feet long that's powered with natural gas, you can eliminate that completely by going to UV, and you also eliminate the afterburners and the solvent emissions. So I think we do need to do a couple examples. I don't have one today, but that question's coming up more and more frequently because I think people want to understand, rightly so.
Awesome, great. I think that's all we have time for. Jennifer, thank you so much. I do want to let everybody that's on the webinar still know that this webinar has been recorded and will be available at the UV EV Technology website. We have a webinar area there. So for others in your company or other people that you think may be interested in it, you can go to uvevtech.com. We'll have it up, I'm sure, by the end of this week, if not sooner, for other people to see. Jennifer, thank you very much for your time today.
Thank you. It's a good time to be in
Appreciate it.
UV. I am very excited about the future of the UV industry right now.
Well, you've always been excited about UV. I know that. I've known you for a long time. But everybody can see Jennifer's information on there as well. And if people have specific questions for her, I know that she'd be glad to take a phone call or an email. So thank you again, Jennifer, and thank you for everyone for joining us.
Fantastic. Have a great day.